Welcome to the third part of switch capacitor circuit design video. In this video, we will look into some of the applications of switch capacitor circuit. First, we will look into a switch capacitor amplifier, which when combined with a sampler circuit, the combination of this switch capacitor along with the sampler will lead to what is termed as switch capacitor integrator. Second, we will look into a switched capacitor circuit that emulates a resistor operation when operated appropriately. We will also get an answer for the question why the combination of the switched capacitor amplifier with the sampler is termed as a switched capacitor integrator once we complete the discussion of the switched capacitor resistor part. The third application will be discussed by looking into the transfer function of an exercise problem, and this will not be done in this particular video. So, as a first application, we will see how the combination of these two capacitors along with the switch SW1 does the amplification process. To understand the amplification process that is performed with these three circuit elements, let us define some initial conditions on the values of the capacitor when the switch is opened. Okay. So, assume that the capacitor CH holds a sampled voltage value which is equal to Vx, and due to this voltage, the charge that is stored on the top plate of the capacitor CH is defined to be plus CH times that of Vx, and the bottom plate of the capacitor CH will hold an equal magnitude of the same charge but with opposite polarities. Okay. Also, assume that the capacitor C2 has no charge that is stored on it, and due to which the voltage across this capacitor is said to have a 0 volt. So one can think of an analogous situation where the capacitor CH could be modeled with a tank, and the capacitor C2 can also be modeled with a water tank. So where the tank number 1 represents the capacitance CH, and whereas the tank number 2 represents the capacitor C2. And also, the water level in these tanks should correspond to the voltage that we have across these capacitors. Since the capacitor CH has a voltage of Vx across this capacitor, one can suitably model the value of Vx with a water level that corresponds to a height that is greater than the ground level. Okay, so I will represent the height to be equivalent to the voltage Vx in this case. And similarly, one can model the 0 volt across the capacitor C2 with a water level that is at the ground level. Also, assume that these two tanks are connected with a pipe that is fixed at the bottom of these two tanks. Okay, and right now when the switch is opened, the tap is closed and no water flows from tank 1 to tank 2. Now when the switch is closed or when the tap is opened, what happens is there will be a flow of water from tank number 1 to tank number 2. So in a way that the water level of tank 1 starts reducing in its height, whereas the water level in tank number 2 starts increasing in the height. The same happens even here between the capacitor CH to capacitor C2, where the charges from capacitor CH flows through the switch onto the capacitor C2, and due to which the value of the voltage across the CH starts reducing, whereas the value of voltage across C2 starts increasing. Finally, as the water level of both the tanks come to some equilibrium height, say for example this is the height, okay, even here the voltage across the two capacitors also comes to some common equilibrium value. Okay, so let me label as V final. The same is reflected in this table, and the charges that are stored after the switch getting closed are reflected as CH times that of V final and C2 times that of V final across both this capacitors CH and C2. In order to derive the expression for this V final, we will apply the conservation of charge principle, which states that the charge can neither be created nor destroyed. So based on this principle, one can equate the charge equations before and after the switch getting closed. Okay, so the charge that we had before is equal to Q1 plus Q2, and that has to be equal to Q1 prime and Q2 prime, where these two charges represents the charge once after the switch gets closed, right? So we know that the value that we had across capacitor CH is Cx times that of Vx, and there was no charge on the capacitor C2, so that's the reason why there is a 0. And the moment the switch is closed, then we had Ch times that of V final, and also across the capacitor C2 we had C2 times that of V final. So I have taken the term V final in common. So from here one can express the value of V final to be equal to the ratio of CH divided by CH plus C2 times that of the value Vx. So one can also write this particular expression in terms of charges rather than the voltage expression just by multiplying C2 on both the sides of this expression. So what I'm going to do is, in order to rewrite this in terms of charges, I'm going to multiply the capacitor C2 on both the sides of my expression. Okay, so when we do so, we know that the product of C2 times that of V final is nothing but our Q2 prime. Okay, and that's supposed to be equal to C2. And now we know that the product of CH times that of Vx is nothing but the charge that we had across the capacitor before the switch getting closed, right? So I'm replacing that with Q1, okay, and that is the value that we had before, and that is equal to C2 divided by CH plus C2. There is an important observation that has to be made here. Note that not all of the charges that I had across the capacitor CH is being transferred onto the capacitor C2. It's only the fraction. That fraction is defined to be C2 divided by CH plus C2. It's only the fraction of this Q1 is getting translated to our Q2 prime. Also, the expression in terms of Q2 prime signifies that to transfer all of the charges from CH to C2 capacitor, one has to have a larger value of C2 such that the ratio of this would become closer to a value of 1. Okay, so that happens only when we have a larger value of C2 in comparison with our CH capacitor. So before making further discussion, let me pose a question of why am I so bothered in the transfer of all of the charges. So the answer to this question is basically the switched capacitor circuit relies on the charge transfer, and one can think again from the tank example that one can raise the water level of C2 tank to increase the voltage across it, thus leading to a high gain from node Vx to Vout node. Okay, so how one can transfer all of the charges from CH to C2? This is obviously evident by looking at our Q2 prime expression, where if I could somehow make this capacitive ratio to be equal to unity, then all of the charges could be translated from the capacitor CH to the capacitor C2. But this necessitates a larger value of C2. But having such a huge capacitor certainly occupies a large area of silicon wafer. Now the question is how one can have a huge capacitor without spending a larger real estate for it. The answer to this question can be derived from the discussion that we had for the frequency response topic, where we discussed about Miller's theorem and the Miller's capacitance, right? So we used in the calculation of the pole of CS amplifier, in which we computed the input pole by applying Miller's theorem across the capacitor CGD, which gets translated into a large capacitor at the input node. I hope that you remember. And an equivalent circuit of that same concept is being reflected here. Here you could see that the capacitor CF is actually appearing as a very large capacitor than compared to the capacitor value. Okay, so this signifies that if I could able to place the capacitor C2 in parallel with a main signal path having a gain of large value, then this capacitor CH, even though it is small, it would appear at the input as a very large capacitance. So let me redraw the structure that we had before. That is a sampling capacitor, followed by that there was a switch, and now followed by this there was a capacitor CF, and rather than having the capacitor CF, what I do is I just translate that with a kind of a gain medium, and I put this capacitor across this gain medium with a value of C2. And now what happens is the capacitance that I would have after applying Miller's theorem would appear as a very large value, as something like C2 times the of 1 plus the gain of the main signal path. Normally this gain medium is realized with some op-amp, and one can have a negative feedback across the C2 such that it appears as a very large capacitor at the negative terminal of our op-amp. Okay. Also, one can tap the output across this node, which I labeled as Vout. Now let us see how the voltage across this capacitor, let me label that voltage to be V2, is developed across this capacitor C2. As one can see that the charge gets translated from the capacitor CH all the way to the capacitor C2 by accumulating the charge carriers over a long time. Okay, so which reminds us some sort of integration process over the charge along a certain amount of time. Okay, so now let us combine this switched capacitor amplifier along with the sampler, and that should lead us to what is known as switched capacitor integrated circuit. Okay, so this is what we have discussed before. We had this part, okay, and the sampler part is something like this, right? So it's a combination of both these parts together creates what is termed as switched capacitor integrator. And as it has been highlighted, there are two switches that are required in this particular design, where the phi 1 and phi 2 are two non-overlapping signals as shown in this figure. Since there are two switches, there are going to be two phases of operation. One is named as sampling phase, the other one is named as integration phase. So let's look at each of these phase operations with appropriate switch conditions. So in the case of sampling phase, the switch phi 1 is basically closed and the phi 2 switch is open. And under this condition, what happens is the input signal Vin would be sampled onto this capacitor CH, and that's the reason why it is termed as a sampling phase. And let us also assume that the voltage across this capacitor CF is basically 0 at the initial condition. And because we are looking into the negative terminal of this Vout, and since there is no charge that is stored across this particular capacitor CF, we have initially a 0 volt across the node Vout. Now during this integration phase, the phi 1 is turned open, and whereas the phi 2 that is turned on. Okay, so due to which whatever the data that is being sampled across our CH is getting connected to this negative terminal of our op-amp, which has a gain of A. And clearly if the gain is so large, then virtually this node and this node will have to have the same potential, and that's where the virtual ground phenomena comes into picture. Okay, so under this condition, what happens is the charges will try to move right from here all the way towards the positive plate of the CF capacitor. Okay, so initially we had a charge that is stored. Okay, so let us assume that the charge that we had before was set to have CH times that of Vn. Okay, and the bottom plate will have the same magnitude but opposite polarity of charge, and now these charges will try to move towards the positive plate of our CF, and similarly there will be a corresponding negative charge that appears on the second plate of the capacitor CF. So the charges that is stored across one end of the capacitor CF is the same charge that we had across the CH capacitor, and similarly a negative charge will be stored here. Now in order to evaluate the expression for V2, we know that the charge Q is basically defined as C into V, out of this we know what is the charge that is available across this capacitor CF, and the capacitor value is basically CF, right? So let me evaluate the value of V2 to be equal to the charge across this capacitor divided by the capacitance value, which is CF, right? So what we have is something like CH times that of Vn divided by CF. And now since Vout is expressed as minus V2, we can rewrite this same expression as something like minus CH divided by CF times that of Vn. So now one can express the gain to be defined as Vout by Vn, and that is nothing but equal to minus CH by CF. Now let's discuss about some of the issues with this particular design. As we know from the digital VLSI design course that different metal layers are separated from each other by some dielectric medium. So in general, one can state that there will be always some sort of capacitance between any different layers, right? So this creates some parasitic capacitance between them. So let me model this parasitic capacitor with our signal path. Okay, so I have a wire, and this wire in general will be separated with some kind of dielectric medium, and that when we visualize with respect to the ground, then this represents the parasitic capacitance. Okay, so now what happens is during the sampling phase, the Vin is sampled not only across the capacitor CH as something like CH times that of Vn, but it also gets sampled across even the parasitic capacitor with a value which is Cp times that of Vn. Okay, and during the integration phase, the charge gets transferred not only from the capacitor CH, but it also gets translated from the parasitic capacitor top plate. Okay, and due to which one can model the Vout as something like minus CH plus Cp divided by Cf, okay, and times thereof the value of Vn that we have sampled, so that the gain has become something like. So why this is considered to be an issue, having this capacitance Cp in our gain expression? The answer to this consideration is basically that the value of this parasitic capacitance in general is unknown, and making the gain of this particular stage to become unpredictable. So we call this kind of circuit as parasitic sensitive switched capacitor integrated circuit, as we couldn't able to completely eliminate the parasitic capacitance. Also this circuit has switches, and when these switches are closed and then opened, we know that there will be always some sort of channel charge injection onto these capacitance, right? So that is again, this circuit doesn't address this particular issue. Apart from the parasitic capacitance issue, we also have one more issue, is that the channel charge injection is not taken care in this particular circuit. Now let us see how to address these two issues by looking into a circuit of this. Okay, so the circuit shown here has already reflected some changes, where in the previous case we had taken the capacitance value or the charge of this capacitor CH from the top plate, and then it was fed back to this capacitor CF. But in this case what happens is the capacitance charges are taken from the bottom plate of the capacitor CH. Okay, so that is the first change that we have done. So before we discuss further, we will see the possible parasitic capacitance that is associated along this particular signal path. So there is a kind of capacitance that we could add across this particular node, okay, which we model it as Cp1, and we can also have some sort of capacitance from this node to towards the ground, so which is again, let me label this as Cp2. And now that we have to add appropriate switches to the circuit to address both these issues, right? So let me choose a different color to add those switches in order to address the issue of parasitic as well as the channel charge injection. Okay, so let me have this particular switch being operated with a phase signal that is related to phi 2, and I have this letter A, and also I will add one more switch that goes in parallel to this second capacitor, second parasitic capacitor, and I operate this particular switch with a signal that is labeled as phi 1A. Note that these two switches, which are operated with phi 1A and phi 2A signals, and the use of these signals should remind you about the discussion that we made in the previous video while we discuss about the bottom plate sampling. Since these switches are operated bit earlier than the corresponding phase signals, they not only reduce the channel charge injection but also helps us to discharge the parasitic capacitance charges before their corresponding switches being turned on. Okay, so it completely discharges this particular path, so no charges from these parasitic capacitance would get translated onto this CF. So thus the addition of these two switches has eliminated both these issues. Now let me redraw the same circuit in a very neat fashion, and that would lead to a circuit that looks something like this. Okay, the same circuit that we had before is just now being redrawn in this particular way. Okay, yeah. So now let me try to discuss about the sampling phase and the integration phase. So it's not the whole phase, it is the integration phase that is happening across this circuit. Okay, so during the sampling phase, it is pretty clear that the phi 1 and the corresponding phi 1A would be on, right? And due to which the capacitor CH would actually sample on this particular Vin onto this with a value of charge that is supposed to be equal to plus CH times that of Vin, and over here it's been connected to the ground. We have the corresponding negative charge whose value is minus CH times that of Vin. Okay, and what we do is we also had said that there is some sort of parasitic component that we have across this node, okay, and even across this node. So now during this entire operation, what happens is, due to this short circuit, there is no charge that is stored across this CP2 capacitor. Okay, so now we know that this phi 1A is turned off a bit earlier than this phi 1A switch, right? So let me remove this on condition so that right now it represents the off condition, and due to which we try to completely eliminate the charge injection issue here. Okay, and now in the case of the integration phase, we know that this phi 2 as well as the corresponding phi 2A switches are closed, right? So under this condition, I have this switch and this switch that has been closed, and due to which no charges would get accumulated on this capacitor plate. Anything that was sampled before, when we try to connect our Vin during the sampling phase, would actually get discharged through this particular path. So nothing is again getting translated onto the capacitor CF. Okay, and as we know that even the switch phi 2 will also have the impact of producing the channel charge injection, right? So what I do is, like, I will try to turn off this phi 2A signal bit earlier than this phi 2 signal, and that's how I can avoid the channel charge injection that happens normally when I don't have this particular switch, right? Yeah, so now that when under this condition, we know that this capacitor CF mimics a very large capacitance at its input, and due to which whatever the charge that I have on the plate that is facing towards the CF would get translated onto this capacitor. So right now what I have is, it is minus CF times that of Vin on the front plate of the capacitor, and the other end will have the opposite charges, which is CH times that of Vin. And again, if I represent V2 as a potential across this particular capacitor CF, then one can write that the value of V2 is defined as something like the charge which is minus Ch times that of V in divided by the capacitance value Cf. And right now when I look for this V out expression, we know that this V out is written as the negative end of my V2 terminal, and due to which I would end up having Ch by Cf times that of V in, and in this case there is no parasitic capacitive component that is expressed in this particular expression. Okay, so now the gain expression would right now would be defined as V out by V in, and in this case we would have a positive gain, means that there is no negative sign here, and this expression is completely independent of the parasitic component that we have. So we call this particular circuit as parasitic insensitive switched capacitor integrator. Next, we will discuss about the switched capacitor circuit that emulates the behavior of a resistor. Before we start discussing the switched capacitor circuit, we will re-look into the behavior of a resistor when driven with two slowly varying voltage sources, namely this V1 of t and V2 of t. Now, since we have considered that these V1 and V2 signals are a slowly varying signal, one can approximate the instantaneous value of this V1 of t to be equal to a constant value, namely V1, and the instantaneous value of V2 of t is equal to V2. Also, let us assume that the value of this V1 is higher than the value of V2. Under such condition, we know that the current flows from the higher potential V1 to the lower potential V2, and one can express the current flow with this following expression, which is V1 minus V2 divided by R. Now we will look at a switched capacitor circuit that is built by making use of two switches and a capacitor. Note that these switches are operated with signal phi1 and phi2, which are operated at a frequency higher than the signal frequency of V1 and V2. So one can say that the clock frequency is almost 100 times greater than these V1 and V2 frequencies. And we will also again assume that these V1 and V2 signals are slowly varying signals when compared to the clock at which we are operating these switches. Then again we can approximate the instantaneous value of this V1 of t to be equal to V1, and V2 of t is equal to V2. Again we will consider the same thing, that is my V1 is bit greater than the value of V2. Assume that the phi1 switches is right now closed, and due to which there will be a current flow from V1 to the capacitor C1, right? So one can write the current flow, which is I1 of t, to be equal to the capacitor times dV by dt, where the dV term represents the change in voltage across the capacitor when there is a current flow. Now one can plot the behavior of this particular I of t on a graph which has been replicated here. So as I said before, when the clock phi1 is on, there is the switch between this V1 and this capacitor C1 is closed, and due to which there is a current flow which is I1 of t, and this I1 of t is basically represented in terms of this exponential graphs. Okay, so again one could note that this I1 of t exhibit a periodic behavior, which means that for every clock period you could be able to see that this exponential graphs repeats itself, right? So whenever we have such kind of periodic signal, then one can write the average current of this I1 of t to be equal to I1 average and 1 upon t integral over 0 to t, and then the value of this instantaneous current, which is I1 of t times that of dt. Also one can see from the graph that this I1 of t is basically non-zero between the value of 0 to t by 2, and it is considered to be equal to 0 when it is between t by 2 to t, right? So due to which one can rewrite this limits of the integral to be equal to 0 to t by 2 times that of I1 of t, and the value of this I1 of t is basically the capacitor C1 times that of dV by dt. So now the dt terms can get cancelled, and now we have to integrate this entire expression in terms of the voltage at time 0 and at time t equals to t by 2. So one would end up having something like C1 divided by t times that of the voltage at time t equals to t by 2 minus the voltage at time t equals to 0. Now one has to evaluate what is the value of the voltage across the capacitor at time t equals to t by 2 and at time t equals to 0, and then they have to substitute their corresponding values at different times at these positions. Now in order to evaluate those voltages at these time periods, let us look across the switching conditions, where the diagram that is shown on the left represents the switching action or the switching condition at times that are equal to t by 2, 3 by 2, 5 by 2 and the odd multiples of t by 2s, right? So now under this condition, it's pretty clear that this phi 2 switch is off and the phi 1 switch is on, and due to which the value of the capacitor voltage would be certainly equal to V1, right? And when we look at the circuit under the condition at t equals to 0, t, 2t and all the integer multiples of t, we could find that the value of voltage across the capacitor C1 would be equal to the value of V2, right? So one can substitute the value of V at time t equals to t by 2 to be equal to V1, and for a similar reason one can substitute the value of the voltage across the capacitor at time t equal to 0 to be equal to V2. So the same is being returned as an expression here. So now let us try to combine both these expressions that we have derived, one for the switched capacitor circuit, the current equation, with the current equation that we have derived for a normal resistor network, right? So we know for a resistor network, for this the current flow could be represented as just I1 is equal to V1 minus V2 divided by R, and for a switched capacitor circuit the average current is represented as something like C divided by T times that of V1 minus V2. So now considering some identical conditions for V1 and V2 for both these networks, then one can equate both these expressions and then rewrite the expression for R to be equal to T by C, or it can also be rewritten as 1 divided by the clock frequency times that of the capacitance. Okay, so it is pretty clear that these two expressions are representing the same phenomena of current that flows between V1 and V2, and that's the reason why one can equate these two expressions and then get an expression for R in terms of the capacitance and the frequency at which it is being operated. So the circuit with two switches and a capacitor basically emulates a resistor network. I also had mentioned that once the discussion about the switched capacitor circuit that emulates a resistor is been discussed, I will let you know about the reason why the circuit of this is called as a switched capacitor integrator. As you could be able to see, a normal integrator that you would have studied in your third semester courses would have a structure where you would have had a resistor R and an amplifier and a capacitor, and the capacitor is connected to the Vout. Okay, so this was termed as an integrator circuit, right? And since this resistance is being replaced with the corresponding switched capacitor circuit, we call this as a switched capacitor integrator. So with this, let me complete the switched capacitor design unit.